Hey physicists, it's Mr. Flowing here, and we are going to move into a new chapter called momentum. So we just finished up energy, and remember that energy is energy is energy is energy, that it can only transfer from one thing to another. So we talked mostly about mechanical energy, kinetic energy, and potential energy, and a little bit of spring potential energy. And now we're going to move into momentum. So when we look at momentum, Sir Isaac Newton came up with his second law where he said F is equal to ma. Now remember that that acceleration is equal to the change in velocity over the change in time. Typically our initial time will count as 0. So I can go ahead and plug this in for my a value here and say F is equal to m times the final velocity minus the initial velocity all over the time, and end up with that. So the next thing I would look at then is if I multiply both sides by t, I get a force times a time on this side, and then distribute my m, I'll get mass final velocity minus mass times initial velocity. So when Newton looks at this, he says, well, that's very interesting because I find that whenever I put a force on an object, that force isn't always constant and it's not always for the same amount of time, but that force will change the motion of the object. Another thing to look at is to look at the right side of this and say, well, when I look at motion, there's got to be more to motion than just the velocity or how fast the object is going. For instance, if I take you out in the middle of the road out here outside the school, and I have my 12-year-old daughter riding her bicycle coming at you going 50 miles an hour, which probably isn't going to happen. And I have a semi coming at you going 50 miles an hour. Which would you rather get hit by? Well, you obviously you're not going to rather get hit by either of those, but if you had to be hit by one of those, you're going to opt for my daughter. Why? Because there's a lot greater of a chance that you can change her motion than that you're going to change the semi's motion. So the velocity isn't the only part that deals with the motion. There's also the amount of mass that is there that is affecting it. And so that really is what this right side of the equation is. So when Newton looks at this, he says, okay, on the left side, we're going to call this force over a certain amount of time impulse. And the symbol for that is going to be a J. So we would say that this whole side over here is J. The unit is going to follow just the unit of force times time. It's not a renamed unit like a lot of the units we studied. So it's just newtons times seconds, and it's a force times a time. Now, when we look at the force times time, think through all of the forces that we've talked about so far. We've assumed that they're a constant force. But if you microize this down, if I come and push on this object, there's going to be just a little bit of force, which is equivalent to this up part, until I'm fully touching the object. And then when I'm fully touching the object, I'm putting the most amount of force on it. And as I push it, then the object moves, and then the object kind of starts moving away, or I stop pushing on it. So I'm going to have that decrease. So everything that we've done, we've sort of taken this graph and we've pulled this down, this side down here, and said, oh, we can just talk about the average force, and we don't have to worry about what this is. Sometimes we can't do that. And so in those cases, what we'll do is we'll say that if you think this through graphically, isn't the force times a time, because we're multiplying, isn't that an area? So that area under the curve is going to be the impulse, which means that if I have a goofy looking graph like this, the spike that's in the middle, then to find a more accurate value, couldn't I say that the impulse is the integral of the force with respect to the time? So that's one of the ways that we can apply calculus to this unit. So the second thing that we'd look at is the whole right side of that equation. And we would say, well, we're going to call this new idea that is the quantity of motion a momentum, or momenta sometimes. So the symbol for it's going to be a P. We don't know where that symbol came from. It just is what we've started calling it. And again, these are not any renamed or redesigned units. They literally follow the units of the equation. So kilograms times meters per second are going to be the unit for that. And again, the definition of momentum is going to be inertia in motion, or the quantity of motion. And the equation for it is going to be literally what you see up here, mass times velocity. So major concept is that in order to change an object's momentum, you have to put a force in a certain amount of time on it. In order to change an object's momentum, you have to put an impulse on it. So impulses change momentums. Okay, that's the major idea with that. So kind of a sample problem here. A 40,000 Newton rocket is at rest when it fires its thrusters. So I'm going to look at that and say, well, that's probably the weight. If I divide that by 9.8, then it will give me the mass. Fires its thrusters. If the thrusters put out an average force, so this is going to be my force over 20 seconds, that's going to be my time. Then what is the impulse the rocket experiences, and what's the rocket's final velocity? Now, there are a couple different things happening here that we'll look through, but since we're specifically only looking at the rocket and not really any of the stuff that's getting thrust out the back, we can take that equation that we had on the previous slide and say, well, the impulse is equal to the change in momentum. Remember that impulse is equal to force times time, and that the change in momentum is going to be mass times the final velocity minus mass times the initial velocity. Now, you might notice from that there are four different things that are all equal to each other in this equation. And when we're looking at it, we'll only look at two of them, and we'll set whichever two we have equal to each other. So when I look up here, I would say, well, this gives me the mass. So I have the mass here, mass here. This gives me at rest the initial velocity. I know that that's going to be 0, but I'm not given the final velocity. So I'm probably not going to use that to begin with. Average force of 5,000 newtons. So I'm given the force, I'm given the time. Looks like I'm going to be using that to begin with. So I have 5,000 newtons times a time of 10 seconds. And that's going to give me what the first thing I can do is find. I can say that that has to be equal to the impulse, which is also equal to the change in momentum. So if I wanted to find impulse, I'm given the force and the time. I can multiply those two and find that value. 5,000 times, oops, not 10 seconds up here, times 20 seconds, which is going to give me 100,000. And remember, the units follow the equation, Newton seconds. Now, part B then, what's the rocket's final velocity? So it looked like we had the mass, and the initial velocity. The only thing we don't know is the final. Well, because we already know that this impulse or change in momentum is 100,000 Newton seconds, can't we set that equal to this side and then solve for that velocity? So the impulse or change in momentum is 100,000. The mass, once we divide this 40,000 by 9.8, we get 4080. And then we have our final velocity minus 4080 times our initial velocity. This whole term goes away. I can divide by 4080 and I'll have a final velocity of 24.5 meters per second. Now, one idea to think through this is that this equation, which I just lost my pen on, this equation up here, it is when you are dealing with one object. It's when you're dealing with a single object. A single object. So when you're dealing with two objects, then we have to move on to a different part of momentum, which is going to be the conservation of momentum, which is also simultaneously happening with this. We have the rocket fuel being thrust out the back going the one way and the rocket being thrust forward going the other way. So when I look at just the rocket, I'm going to do this. But if I were to look at the fuel and the rocket, that's when I would have to deal with the conservation of momentum. Now, law of conservation of momentum. Remember that the conservation laws are typically cannot be created or destroyed. Okay, I say typically because there are some, like the conservation of charge, where we can create and destroy charge, but the net charge has to stay 0. So the conservation of momentum, conservation of energy. We cannot create or destroy momentum. We cannot create or destroy energy, which means that we end up with this marvelous equation that is pin equals pow. Momentum in equals momentum out. And the key idea for this is that it always has to do with collisions. Anytime you have two objects colliding, no matter how they collide, we have to talk about the conservation of momentum. Interestingly enough, conservation of momentum is one of the laws of physics that it stays constant whether you are looking at macro physics or whether you are looking at micro physics. So when we started doing the quantum physics, we found that there are a whole lot of physics laws that break down in that big particles versus, or big objects versus little particles. But the conservation of momentum is not one of those laws, and the conservation of energy is the other law. So those two are really a pillar of all of physics, whether you're talking Einstein physics or Newtonian physics. Now, one thing we have to talk about if we're dealing with energy is there are two types of collisions too. We have an elastic and an inelastic uh, collision. An elastic collision is where the energy is conserved, and an inelastic collision is where energy is lost to heat or sound or some type of energy we can't get back. So realistically, there is no such thing as an elastic collision. I mean, the closest thing that we would talk about in the scope of this class is maybe like a billiard ball set, pool table. So you have the pool ball comes towards another pool ball and hits that pool ball. That almost all of that energy is transferred into the next pool ball. Now you can still tell that some of that energy is not because you hear some of that cracking sound whenever they hit. So there is a little, like a little bit of energy that's lost into that. So then when we go on, let's talk about a sample problem. An ice skater with a mass of 55 kilograms throws a snowball while standing at rest, and the snowball has a mass of 20 grams and moves straight out with a horizontal speed of 20 kilometers per hour. So the first thing that I'm noticing is that we have a mix-up of units here, right? So ideally, we want to put everything into standard physics, into kilograms, meters per second, and then that will make things easier. Now, you'll notice in the conservation of momentum law, if we keep them all in the same unit, it won't matter because they're going to cancel out. But if we are doing the impulse and momentum, the FT, MV, we have to make sure that our units kind of match on that. So neglecting friction and assuming the skate blades are parallel to the direction of throw, describe the skater's resulting motion in detail. What is the skater's final velocity? So think through this. I have my skater here. So my skater's standing here and they throw this snowball this way. So if you conceptually think through, if I'm just standing here, I'm just holding the snowball, what is my momentum n going to be? What is our both of our velocities? They're both zero, right? So isn't our momentum in zero? Which means that as soon as I throw my snowball this way, doesn't my momentum that pushes me have to cancel out the momentum of the snowball this way? Which means that I'm going to have a momentum that goes the other way. It has to be an equal and opposite momentum. Now, if I throw the snowball, is my velocity going to be as big as the snowball's velocity? And you can kind of conceptually think through that. It shouldn't be. Why not? Because if the mass of the snowball, which remember, mass plays a difference in the quantity of motion, if the mass of the snowball is way, way less than me, then ratio wise, shouldn't my velocity be way, way less than the snowball's velocity? So how would I solve for what that skater's final velocity is? I'm going to do the conservation of momentum. Momentum in equals momentum out. I can say mass times velocity. I'm sorry, the momentum of the skater plus the momentum of the snowball in is equal to the momentum of the skater plus the momentum of the snowball out. Then I can say, well, the skater and the snowball both had zero velocities to begin with. I was given the mass of the skater, which was 55. I was given the mass of the snowball. I converted that into 0.2 kilograms. And then I also converted that kilometers per hour into meters per second. So now I have an equation that has everything in it except for the velocity of the skater. And when I solve, I'm going to get the velocity of the skater to be 0.0202 meters per second. Again, notice how way much smaller that velocity is than that velocity because the skater has a much larger mass. Now, you could conceptually think through it too. If their momentums have to be equal and opposite, so here's the momentum of the velocity of me equals the momentum, or the mass, sorry, the mass and the velocity of me equals the mass times the velocity of the snowball, except in opposite directions. So I'm going to put a negative there. Now, if the snowball has a really small mass and a really big velocity, and I have a really big mass, then what has to happen to compensate? I'm going to have a really small velocity. So I hope that makes sense. Okay, moving right along. Now, let's do one of these terrible, horrible, extremely awful, lots of work problems. This one involves energy. So a glass ball of mass 200 grams is traveling east at 10 meters per second. So a glass ball here that is 0.2, it's traveling east at 10 meters per second. And I'm going to put a G for glass here. And a steel ball, so I guess I'm going to have another one over here that is 0.4, is traveling toward the glass ball at 20, so negative 20. They collide, and we want to know what the speed and direction of both the balls immediately after undergoing the elastic collision. So here's going to be my momentum in. Then I'm going to have zero point 0.2 times some velocity of the glass plus 0.4 times some new velocity of the steel. That's going to be my momentum out. So if I look at this, I can say my momentum in equals my momentum out. Steel momentum plus glass momentum equals steel momentum plus glass momentum in and out. And then MV plus MV equals MV plus MV. I can plug in those numbers like I have up here. 0.2 times 10 plus 0.4 times negative 20 is equal to 0.2 times the final velocity of the glass plus 0.4 times the final velocity of the glass. So now I want to simplify. I'm going to multiply all of this and add on the left side. The next thing I will probably do is divide by a 0.2 just to simplify things here, and that gives me this equation. Now, that's not really a good answer because it doesn't give me the velocity of either of those. Now, so the problem becomes then, if I have two unknowns, what has to happen? I have to have two equations, right? So where can I come up with that second equation? It does say that there is an elastic collision going on there, which means that don't we have a conservation of energy? So what energy is involved if there's a motion of the objects? It's got to be kinetic energy. So I have a kinetic energy in equals a kinetic energy out, right? EIO, energy in, energy out. And we can say kinetic of the steel plus kinetic of the glass equals kinetic of the steel plus kinetic of the glass. And 1 half mv squared plus 1 half mv squared equals 1 half mv squared plus 1 half mv squared. And then we can plug in values. And you'll notice too, I could get rid of each of these half values because they're all the same. Now, can I get rid of the m's? No, because they're not the same. One is 0.2, one is 0.4. Can I get rid of the v's? No, because they're all different, right? So then after you've gotten rid of those halves, we can plug in the mass, 0.2, the velocity 10, 0.4, negative 20, 0.2, 0.4. Now, can you see where this is going? If I simplify this, I can simplify all this side, then again, divide this by 0.2. Hey, what happens now? Don't I have two equations and two unknowns? And this is where it's so beautiful. So now, what if I solve this one over here? Probably because to me it's easier because I don't have the square root value. So I end up with 30 plus 2vs. Can't I plug that into this equation? And that's where that comes from. So 900, the 30 plus 2vs squared plus 2vs squared. And guess what we're going to have to do? We're going to have to FOIL this inside part, the squared value. So 900, 30 times 30 is 900. 30 times 2 is 60. Yeah, 30 times 2 is, I hope I did that right because that just doesn't seem right whenever I look at it. Okay, so I'm back and I was looking at that and figured out what was wrong. First off, there were two things wrong with that. Well, one of them's not technically wrong. So you'll notice that up here in this first equation, my negatives went away. Now, why would they have done that? Because I was anticipating this move down here where I'm going to square it. So whenever I square it, if I have double negatives, remember it's the same as having double positives. So technically speaking, I wouldn't necessarily get rid of those negatives, and they will become important later when I plug back in one solution. The second thing that was wrong that was off of this guy is this is not 600. This is 120 VS. And so I made that correction here in my slide. So 120. So I can get rid of the 900s then. I can take that 120 VS, I can add those and get 6 VS squared. And if I simplify that, I end up with dividing by 6, I get 20 VS plus VS squared. Pull out a VS and I get 20 plus VS times VS equals 0. Super, super easy solution then, right? Where I can say that the steel ball either has a velocity of negative 20 or a velocity of 0. Then I can take that value, plug it up into this equation, and find out what my glass ball velocity is. And if the steel ball's velocity is negative 20, the glass ball's velocity is positive 10. If the steel ball's velocity is 0, the glass ball's is negative 30. So the question then becomes, well, which one of these is correct? Now, think through it conceptually. There are two ways you can think through this. First off, is the steel ball after the collision going to have the exact same momentum that it did before the collision? 999 times out of 1,000, the answer to that is going to be no, it's not. So you know that it can't be the negative 20. Now, another way to think through it is if the steel ball is still going negative 20 to the left, can the glass ball still be going positive 10 to the right? There's no way that they could hit each other and just pass through each other. So it can't be that solution at all. So what we have to know from that is that the steel ball is going to stop and the glass ball is going to rebound back the other way, going at negative 30 meters per second. So this is just a fun example of where we would have an elastic collision where the energy is conserved. We can set up the conservation of energy equation and simultaneously solve it with the momentum in order to find out what those velocities are. So, in general, remember, major idea is that in order to change an object's momentum, you have to have an impulse acting on it. The impulse is equal to the change in momentum. And if we're dealing with one object, like we could just be looking at the glass ball and say, well, how much force was acting on that? In which case, we could say the force times time equals the mass times velocity, and all of that dealing with just the glass ball. But if we're dealing with the two objects that are colliding, then we have to deal with the conservation of momentum.